Hello, welcome to the latest in the series of AGR's educational short videos. The topic for today, we're going to talk about converting from 100% virgin material, PET material, to some percentage or 100% rPET. This is being driven by moves throughout the global industry, the global packaging industry, to increase the percentage of recycled material in all forms of packaging. The effects of converting to rPET on a global basis for the industry, it creates many challenges. So it's not just a simple matter of switch from virgin material to rPET. The properties of the material in many ways are much different. You have to look at setting up with the blow mold or your oven profiles. They're going to be different. The material stretches slightly different than virgin material. So it creates a lot of challenges in making that conversion. The goal would be to make minimal changes to the 100% virgin recipe, assuming that's a well-centered, capable process to start with. So the success is that you want to wind up with, number one, a good-looking, attractive container with no visual defects. Two, more importantly, a well-performing container that has good top load values, burst strength values, volume expansion, your section weights are in spec. So from a performance standpoint, you're making a container that's completely 100% at its nominal values of the bottle specifications, so that you're making a container that's going to perform equally as well to a 100% virgin container. That's your first and foremost goal, a combination of a good-looking container that meets all the criteria from a performance standpoint. The color of the preform, the color shade or hue, changes pretty dramatically with rPET. rPET, as you're converting the recycled material back into resin to make the rPET preforms, there's a natural yellowing that occurs because of oxidation. So they have to put a colorant in, typically a carbon black toner, which changes it from a kind of a yellowish shade to a smoky gray blue shade. That's the same agent that they put in resins for a rapid reheat resin to be able to heat it more quickly. So it significantly increases the energy absorption of the material. So it has a very big effect on the overall process, the blow molding process. So that color has a really big effect, and variability in that color has a really big effect in the ultimate consistency of your production. Because of the fact that that colorant absorbs energy more quickly, one of the primary things it affects is preform temperature. We typically see a decrease in preform temperature being necessary of anywhere from 5 to, we've seen as much as 8 or 9 degrees C, needing to lower that preform temperature by that amount to make the same container with the same material distribution, same performance. So that has a very significant effect on preform temperature. To start with, you want to take your existing, confirm that your existing recipe for virgin produces a well-centered container, well-centered, high-performing container that meets all the specifications. So you start with that, make a copy of it, name it with rPET somewhere in the name, and then load that. So that's what you're going to use as your basis. So the next step would be to run your hopper with the virgin preforms, run that out empty, and then load in the rPET preforms. This gives you a clear differentiation, a clear demarcation between running the virgin and the rPET. So the first thing to do is just start running with that, what is the virgin recipe with the rPET preforms. The first thing to look at is the preform temperature. So if you see that it's coming out very hot, you want to initially make some changes to the startup percentage. That's the one thing to do. You may need to make some changes to the lamp configuration, turning off a lamp in each zone to lower the amount of energy that's being absorbed. So once you get the preform temperature at its coming out at its set point, the original set point, you want to reject some preforms and check them for malleability. And when you squeeze them together and squeeze the walls together at that set point temperature, you should get a little tackiness. They should stick together for a second. That's a pretty good indication that you're in the right ballpark of where you want to be of heating the preform, heating the material to stretch properly. So once you know that your preforms are coming out at the same temperature that the original recipe set point was at, after you check the malleability, you want to blow some containers and pull those samples off. And the first thing is to do a visual inspection. And are you seeing white feet purl in the base of the container, which would indicate you're either cold stretching or you've got your material distribution way off and you're overstretching in that region. You'd want to look to see if there's a ring of material in the neck or a puddle of material in the base. So you're looking for visual defects of the container, which are obvious things that you know you need to make some process adjustments to correct. If it looks overall acceptable, then the next step is to pull those samples and do section weight tests, do top load, do burst pressure and volume expansion. So do some of the performance tests to see how close is that bottle to its nominal design parameters for all of those different factors. If you see that you have a problem with any of those, the section weights are off, then you want to begin making some changes to oven lamp zones, pre-blow pressure, pre-blow start time, and the preform temperature set point. You'll be making those one at a time, pulling samples and rechecking to see that you're making a bottle that's in spec. In some cases, some of the extremes we've seen where you have to lower the preform temperature by 6, 7, 8 degrees, you're probably going to have to make some other changes, as I mentioned, possibly turning a lamp off in each zone. All the while as you're doing this, you want to make certain that your oven lamp percentages remain at 70% or above, and that your overall oven output is typically in the mid 80% range. That's important for getting proper infrared energy penetration into the preform for proper heating of the material, and also to make sure that you've got your process is capable, so if the temperature in the plant gets colder, you've got adjustment room to increase that oven output to compensate for that, or if it gets warmer, there's some room to decrease it. Once you've made your process adjustments, you want to pull samples and check to confirm that your bottles are at your nominal values for section weight, top load, burst pressure, volume expansion. On a CSD container, I usually argue that that is probably the most important performance factor because it tells you so much about the overall bottle process, the material, and your material distribution. So once you're at a point where you're getting consistent values that are in that center zone, then you can begin running production and start continuing just to monitor it and then see how it performs in the filler and the labeler. So in conclusion, taking a controlled stepwise approach to converting from virgin material to rPET really is pretty straightforward. Starting with your base virgin recipe, emptying out your hopper, running your rPET, seeing where it's at, adjusting preform temperature, all the while taking samples to check performance, and then making any process adjustments that are needed to get your performance factors on their nominal values, and you have a good looking and well performing container. Thank you.